Okay, everyone, let's get started. Welcome back. Remember that last time we went over perception of motion. We talked about stroboscopic apparent motion. And then we got started on tracking. And in particular, I'm looking at head tracking. And we got into the case of integrating gyroscope measurements, which are providing readings in terms of angular velocity, so radians per second. And in the two-dimensional case, I gave a simple example, imagining a merry-go-round or a top spinning. And if you get measurements of that, here's the example of the measurements, just scalar measurements. Essentially, it's rotation with respect to the vertical z-axis. So you have omega k hat at each step. You have delta t, which is 1 millisecond for our examples we've been giving. And so we just have this very simple update. We calculate some change in theta estimate and just start adding. We add in each step here and just keep repeating this equation over and over again. And then I showed you that the three-dimensional case is very similar, except that we switch everything to Quaternions. And so the replacement for this omega k delta t is constructing a quaternion that will give you the change that occurs during delta t. It's an entire small rotation about some particular axis vk, and the total amount of rotation is theta k. So these together become delta q sub k hat. I put quat here in front of it to make it look like a constructor from a class. Let's say, suppose you have a quaternion class in C++. So just to emphasize that there's a quaternion that's constructed here. And remember, these two parameters come just directly from the gyro reading. If you just normalize the omega x, omega y, and omega z components, you would get the axis of rotation for here, and then the magnitude of that original omega x, omega y, omega z vector will give you the total amount of rotational change estimated for that 1 millisecond. Right? You gotta remember that? Right. So if we do this over time, what we mentioned at the end of class is that we end up with what's called drift error. So the problem over time is called drift error. So it's a gradual divergence between the true orientation and our estimate of the orientation. And these will gradually get worse and worse, especially because most of the errors that we have in this process are systematic. They're due to calibration difficulties in some way. So it may be that the gyro along the x-axis always gives you a reading that's an overestimate by a certain amount, and that will just continue to increase the drift error linearly. All right. So if we think about drift errors in 2D, I could say that at each step the drift error, let's put d sub k for drift, is the true orientation theta k minus theta hat k. In this case, it's a signed drift error. And in 3D, we could say that the drift error, in this case, I want to subtract two orientations, but if I'm using quaternions, I have to use the algebra of quaternions, and we have to also remember non-commutativity. So I want to take my true quaternion minus the estimated quaternion in defining this drift quantity. So let's suppose the true quaternion, or true orientation of the head, if that's what you're estimating, is q sub k. Then I want to essentially subtract off my estimate, q hat minus 1. I guess I could go in either direction with this as well. I'll get two different results, but they're both measurements of the error, right? So depending on which way I want the sign, I could have also written q hat minus 1 sub k, quaternion product q sub k, right? It's non-commutative. It will give me an error in the, essentially the other direction. Is this okay? So the concept here, I mean, normally, for most problems you've dealt with in engineering, you may talk about a scalar error, right? There's some real valued error. It's non-zero, and therefore needs to be reduced or eliminated in some kind of way. You may have considered a vector of errors before. Just keep in mind that the drift error in this three-dimensional case here is an entire 3D rotation. So it is a quaternion. And so if you apply the inverse of that, you will be correcting the error. And so So this one, it's a kind of an unusual quantity to have for an error. So the errors that we get, the drift errors, tend to accumulate over time. So drift error, if left unchecked, may grow at a linear rate, may grow faster than that, may grow slower than that. It depends on a number of things, but very commonly if you go take plots of the drift error of a gyro after doing integrations, you'll very often see linear behavior, especially for a fixed angular velocity. If you go faster or slower, the rate may change and these curves may go up or down. And then there's also noise factors in some as well. If the gyro is very well calibrated, then it may have a different behavior that's mainly dominated by, say, white or Gaussian noise. So what we want to do next is try to use other sensors to try to reduce this drift error back down as close as possible to 0. So correcting for drift errors. So two key points for correcting for drift errors. One, use another sensor or sensors to provide a world reference. So in other words, some kind of reference information with respect to the world frame as the body is rotating, taking its measurements from its body frame. And then we want to somehow gradually apply corrections. And this is a difficult problem. It has to be fast enough, whatever corrections we apply, they need to be fast enough to fully compensate for drift. But at the same time, they need to be slow enough to avoid simulator sickness. Or other kinds of disorientation or discomfort. So suppose, for example, you're running along for 30 seconds and then you get a sensor reading from some other sensor that's not a gyro that tells you you're off by 30 degrees. Do you just all of a sudden apply that? Right? Or do you gradually apply it within the course of a second? If you do that, you can perceive that the world is all of a sudden tilting, the virtual world will be tilting. So you have to provide it in a very gradual way. It may be the case that your gyro is so bad and this drift rate grows so fast that there's no way to compensate for it without causing some kind of sickness. So it could be the case that it's so sloppy that you cannot compensate quickly enough and still be within thresholds. It turns out we're very fortunate in today's world of MEMS-based gyroscopes that appear on our top-of-the-line smartphones these days, that the gyro quality, especially if the gyroscope has been very well calibrated, especially for temperature dependence and other factors, then the growth rate ends up being slow enough so that it is possible to compensate for this without, as far as we can tell, without perceptual side effects causing simulator sickness. So we're very lucky to be in this kind of regime today where we can in fact accomplish this. So let me give you some of the technical details of how these corrections work. So we would like to divide the error up into two components. So separate rotational drift error into two components. One is called tilt error, and this can be viewed as a combination of pitch plus roll, right, tilt error. So has the world become tilted? So it may be the case that my virtual world, as I'm doing the head tracking, appears to have a tilt in it, right? So this can be any kind of pitch or roll. Imagine just a few degrees of it. So tilt, same kind of thing you might imagine in the real world, corresponds to cases in which you're not aligned with gravity, right, where the surface that you're walking on appears to be tilted. A ball will start rolling in any direction, any one of a number of directions, if there's a tilt to it. This is separate from another error, which is the yaw error. It's the remaining component. And this has to do with losing track of which direction you are facing. Right? So the yaw is the remaining component. We had troubles with this early on at Oculus, for example, because when people were playing a cockpit game, so imagine you're sitting inside of a car and you have a dashboard, or you're sitting in an aircraft or spacecraft and there's a cockpit. After 10 or 20 minutes of play, the cockpit starts drifting to the side. And you can sit in your chair, and if you have a rotating chair, you could rotate with it without even realizing it, and before too long you're tangled up in the cables because of this yaw drift error. So it ended up being a very serious problem. So the reason why they're divided into tilt error and yaw error is because the kinds of sensors we use to correct for these tend to fit very naturally into these two categories. So I'm going to first talk to you about how tilt error is typically corrected, and then we will go in a little bit into yaw error, but it works very similarly. All right. Now, to correct tilt error, what we would like to have ideally, we need, or would like to have, an up sensor. In other words, a sensor that measures which way is up in the global frame. That would be nice, wouldn't it? Because that's what the definition of tilt is. It's some mismatch with respect to up, right? Some deviation with respect to up. And then in the case of yaw error, we would like to have some measurement of which way was forward initially, and we'd like to keep maintaining that. So we need something that behaves like a compass. Now it turns out that in the real world, we can never get either one of these very precisely. We do not get perfect devices that will give us these. So what we're going to use in the case of measuring tilt error, instead of our up sensor, we're going to use a linear accelerometer. And in the case of, instead of having a compass, in case of this, we're going to instead use a magnetometer, which measures magnetic fields, which might include the Earth's magnetic field, and it may include many other fields superimposed together. So let's suppose we have this perfect up sensor, and it's accomplished by a three-axis accelerometer. So it's measuring x, y, z components as meters per second squared. And then I want to take a look at this in a particular coordinate frame. So let me draw out a coordinate frame here. I have x, y, z coming out as usual. And then I'm going to draw on this frame, and then I will say what the frame represents. Let me see here. I have this vector here. I will call it A with a hat on it representing some kind of estimate, which is a measured acceleration. And this, what I would like this to represent, is my current estimate of my orientation, but the inverse of it applied to the accelerometer readings. This should be the current accelerometer reading. So in other words, on the device, on the sensor itself, which is moving with your head, I have an accelerometer. It's measuring meters per second squared acceleration in the x, y, and z directions. Let's assume, just for a moment, and I'll return back to this assumption, let's assume that your head is actually not undergoing some linear accelerations at present, or the sensor is not undergoing linear accelerations. If that's true, what would an accelerometer measure? Right, just gravity, right? Just acceleration due to gravity. So let's just assume it's going to measure that component alone. If I take that measurement's going to be done in the body frame, because that sensor is attached to the body. But if I believe that I've constructed a nice estimate, q hat sub k, of the transformation that will move the body into its frame from the world frame, then I should be able to take the measurement and transform it back into the world frame using the inverse. So that's what I do. So I take the measurement, I bring it back into the world frame, and if my sensor is correctly reporting up, and if my estimate of this orientation of the body is correct, then this yellow vector should be aligned perfectly with the y-axis. Instead, what typically happens, it'll be off by some amount. So the amount that it's off, I will write as phi. And this will be some estimate of the drift error. I suppose I should put a hat on that if we keep using hats for estimates. All right, so if that's the case, what I would like to figure out is what needs to be done to bring those two into alignment. And so you can look at it either way. You could try to bring the yellow arrow up to the white y, or rotate the coordinate frame y to line up with the yellow arrow. I need to take a look at what should be done here. And so let's take a look at this A vector, and let's write it out as A equals, and remember, this is already transformed. I've already applied this Q inverse to it. I have three components, A x hat, A y hat, and A z hat. Right, so there's three components to it. And now what I would like to do is perform a rotation that does not cause any yaw to change. I just want to change pitches and rolls. In order to do that, what I want to do is find an axis in the xz plane. Right, so if I can find an axis, and I always do rotations about axes that go through the origin. So just imagine that I need some axis that goes through the origin. It also lies entirely in the xz plane. So when I grab onto that axis, I can perform a twist that will bring these two together. Right, I'll grab on the axis you can imagine is attached to maybe the white, let's say, and it just performs a twist that lines it up with the yellow. So that's what I want to do. So easy way to do that is I just take this A vector and I project it down into the xz plane. So let's try that. So I project down into the xz plane. That gives me a vector. I'll call it v tilt, which would be the tilt axis. Oh, sorry, that's just the projection, not yet v tilt. Sorry, I need to do one more operation. This axis here is A x hat, 0, A z hat. Correct? So I just get a 0 component for the y. Now I want to pick a perpendicular vector to that, and since I'm only really dealing with 2 dimensions now, I want to pick a perpendicular vector. So you may remember, you can just simply swap the 2 coordinates and negate one of them, right? Which one you negate will tell you which direction the vector points. So I want to obtain the following axis. I want this one, which should be perpendicular. And I will call that one v tilt. And that will be A z hat, 0, A hat x, minus A hat x. So I got to negate one of them in order to get an orthogonal vector. So this will be the tilt axis. What I want to do is grab onto this and perform a correction by performing a rotation. Now, as I said, I do not want to perform the entire corrective rotation at once. So let me give you a very simple way to do the correction, and it's equivalent to many alternatives. Simple way to correct is to use what's called a complementary filter. So in this filter, we will have what's called a gain, or gain coefficient, alpha greater than 0, but alpha very close to 0. So for example, maybe alpha equals 0.0001. The particular rate of alpha, the particular value of alpha is going to depend on the sampling rate, which is delta t is 1 millisecond for our continuing example we've been talking about. So now, in order to correct for drift in each time delta t in each step, we have now a corrected orientation, which will be some quaternion we generate, v tilt. And at this point, I could apply the entire theta here and try to correct for it. What's going to happen, though, is that it's very likely that my theta is a noisy estimate, and it's too much correction to apply all at once for perceptual reasons that I talked about. So if you try to apply this, and I did some experiments like this in the code myself, I tried applying corrections all at once, you end up with a very unstable view. The orientation is just changing wildly all the time. So this is where we use this gain coefficient, so it's alpha times phi. So that'll perform a very tiny rotation in each step that's making progress in the right direction. And then it just continues like this. So you end up with a very stable representation of the orientation, right? You end up with a very stable view. But this alpha needs to be large enough so that it's applying the corrections fast enough to compensate. One of the things we did was perform experiments with a robot moving the sensor through space at different angular velocities to determine upper bounds on the maximum amount of drift error that could occur so that we could set the coefficient large enough to overcome that. And luckily, as I said, it was still within thresholds so that it did not seem perceptible or sickening to the user. So we got very fortunate with that. So we apply this correction to the previous estimate, Q hat. Questions about that? All right, let's see. So what I want to mention now is a problem with the accelerometer. Yes? That's a good question. So every time I go through this, I have to go back and ask myself, is it minus or plus based on the way I've set up all the coordinates, right? So one of the possible ways to change it from plus to minus depends on which way I've made this axis, right? One of the ways it could be plus or minus depends on whether I'm rotating A or rotating this, and am I applying the inverse or the forward. I checked it this morning, and I believe it's positive. But maybe we should go back over it again maybe during the break and see if we find an error. So unless you're convinced it's minus, I think it's correct in plus. But again, it is quite possible that somewhere along the way I may have inverted a step. If you write the code for this, you very quickly see that you've made a mistake, and then you can go back and check each one of the components. Of course, I never suggest encoding just changing signs until it works, because you'll end up with quite a mess after doing this 2 or 3 times. But I believe it's positive in the way I've set it up. But I admit I might have made a mistake because there's several steps in a row here, each one of which could flip the sign. So, I think in this case, I'm applying an additional rotation to move this frame towards the yellow. So that's why I think it's positive. Yep. All right. That's very good, though. I was anticipating that question. Someone usually asks, and I usually ask it myself. I'm like, have I gotten the sign right? It's very, very important to see that, to check that. All right, other questions? So let's see. One big problem with this, as I mentioned, is that the accelerometer is not a perfect up sensor. Let me put that here, I guess. So problem. The accelerometer measures the following vector sum. There is the up part, which is 9.81 meters per second squared, but there's also the true linear acceleration. Let me draw it off in a different direction here. There's also the true linear acceleration of the body, so linear of the body. And so it's actually the vector sum of the two that's getting measured by the accelerometer. Right, this is what's measured. So what do you do in that case? Well, you could invent some simple heuristics. I've seen in some published papers, for example, someone might say, well, if the magnitude of this yellow vector, the part that you're trying, the measurement that you get, if it's close to 9.8, within some small epsilon of 9.8, then assume that this part must be 0. Is that a reasonable assumption? Well, it's not bad, except I should be able to move downward, and that compensates for some of gravity, right? Because if I were free falling, I would completely cancel off this up vector. So I should be able to reduce the up vector by moving down in some way. But I can also linearly accelerate while doing that, and I should be able to get it so that I convince the drift correction system that makes this assumption that the world is tilted by a large amount, right? So you end up with this kind of situation of making some heuristics to try to separate out these two vectors so that you can get a reliable up reading. This particular assumption by itself won't work all the time. It's reasonable in many cases, but you have additional information because you also have access to the gyro, which is giving you the angular velocity. So if you all of a sudden get an estimate of up that's extremely far, you know, it's very, very different from what you previously believed up was in the global frame, and it happened in a short amount of time, right? You can very easily also compare that with the gyro history because you're integrating the gyro forward and the drift rate is not too bad in a short amount of time. So you could give very low confidence or rule out very unusual accelerometer readings that seem to indicate that up is, say, 30 degrees off from what you once believed. Now, if the person continues moving their head very wildly and violently for a very long period of time, there may be no good way to compensate. And you may be able to kind of fool the system into believing that there's a significant amount of tilt before it's able to go ahead and correct that. So, so that's one of the strange outcomes of that. And it's not really the fault of any engineer in particular. It's a problem of the fact that when we measure accelerations in some moving frame, we always get this vector sum, and there's no way around that. And we're just trying to separate it out. We do not have the ideal up sensor, and no one will be able to make one, right? Purely based on inertial measurements.